Welcome back, everyone, to the Deep Dive. This time, we're going to be exploring something pretty fascinating, and I'll be honest, a little bit mind-boggling for me, too. The world of four-dimensional topology.
Yeah, it's definitely a wild ride.
And, some of you might be thinking, topology? What does that have to do with, AI and ML research? Well, that's exactly what we're here to explore.
Right, and it might seem like these are completely separate fields, but there are some really surprising connections. We'll be looking at some cutting-edge research in four-dimensional topology, and specifically something called exotic smooth structures.
Exotic smooth structures. Okay, that sounds intriguing, but I gotta admit, it's a bit outside my usual wheelhouse.
I hear you, but it's not as complicated as it might sound. Think of it this way. Imagine you've got two shapes, and they look exactly the same at first glance, like you could mold one into the other without any cutting or gluing. We call that homeomorphic in topology. But then, imagine you zoom in, way in, like at the infinitesimal level, and you suddenly discover that these two shapes have a totally different texture. They're smooth in completely different ways. That's where exotic smooth structures come in. There are these wild, unexpected differences that are hidden beneath the surface.
So it's like they're wearing different disguises. They might appear the same on a large scale, but then up close, they reveal their true exotic nature.
Yeah, that's a great analogy. And it turns out these subtle differences can have huge implications. Especially when we're dealing with four-dimensional spaces, things get really interesting.
You keep mentioning four dimensions. What's so special about dimension four in this context? I mean, we work with high-dimensional data all the time in AI and ML, so why is four such a big deal?
Well, dimension four is kind of this mathematical no man's land.
Yeah.
In lower dimensions, one, two, and three, we have a pretty good handle on how to classify shapes, how to tell them apart. And then in higher dimensions, five and above, there are these powerful tools like surgery theory that let us break down the problem and make sense of things.
Okay.
But dimension four, it's like the wild west of topology. None of the familiar tools quite work right, and we're still struggling to understand even the basic rules of the game.
It's like we hit this dimension four wall, and suddenly all our intuition about shapes and spaces just goes out the window.
Exactly. And
Yeah.
that's what makes it so fascinating, right? It's a frontier where we're still making these fundamental discoveries about the nature of space itself. And some of those discoveries, believe it or not, have the potential to shed light on challenges we face in AI and ML.
Okay, you've definitely piqued my curiosity. But before we dive too deep, let's unpack the basics a bit. What exactly are these exotic smooth structures, and how do they relate to the challenges of, say, navigating high-dimensional data spaces in machine learning?
All right, so in topology, we're not as concerned with the precise shape of an object, but rather how it can be deformed.
Mm.
Can you stretch it, bend it, twist it, into another shape without tearing or gluing?
Yeah.
If you can, then those two shapes are considered topologically equivalent or homeomorphic.
Right.
It's like molding clay. You can change the shape, but the material is still the same.
You're right, like that classic example of a coffee cup being topologically equivalent to a donut.
Exactly. Now, smooth structures, they take this idea a step further. They tell us how smoothly we can deform one shape into another.
Okay.
So two shapes are diffeomorphic if there's a smooth invertible map between them.
Okay.
Think of it like a perfect distortion-free transformation. Every little bump and curve is preserved perfectly.
So diffeomorphic means you can not only mold one shape into the other, but you can do it without any wrinkles or creases.
Precisely. And here's where things get really strange. In four dimensions, there are shapes that are homeomorphic, meaning they look the same topologically, BU, not diffeomorphic. They have different smooth structures.
So they're like those disguised shapes you mentioned earlier. They might look alike at first glance, but when you examine their smoothness, you realize they're fundamentally different.
Yeah, that's the idea. And these are what we call our exotic manifolds. They reveal this deeper level of structure to four-dimensional space than we might initially suspect.
And these exotic structures, they're not just mathematical curiosities, are they?
Mhm.
You're suggesting that they might actually have some relevance to the kinds of challenges we face in AI and ML.
That's right. Think about the challenges of navigating high-dimensional data spaces. In machine learning, we're often dealing with data sets with hundreds or thousands or even millions of dimensions.
Yeah.
It's incredibly difficult to visualize or even conceptualize such spaces, and yet hidden within those spaces are patterns and relationships that we're trying to uncover.
So you're drawing a parallel between these exotic smooth structures and the hidden structures within high-dimensional data, like maybe we're overlooking crucial information because we're not looking at the data with the right kind of lens.
Exactly. The existence of exotic smooth structures in 4 dimensions suggests that there might be subtle hidden structures within high-dimensional data that we're not yet equipped to detect or understand.
Okay, now I'm really starting to see the potential here. But how do we even begin to grasp these exotic structures? You mentioned that dimension 4 is particularly challenging. So what tools do mathematicians use to explore this strange world?
Well, one of the key insights comes from something called the quark theorem. It tells us that these exotic pairs of 4 dimensional shapes are related by a sort of cut and paste operation. Imagine taking one shape, cutting out a specific piece, which we call a quark, and then gluing it back in, but with a twist.
Interesting.
This seemingly simple act can actually change the smooth structure of the entire shape, creating an exotic pair.
Quarks that can twist the fabric of space. That sounds like something straight out of science fiction. But how do these quarks relate to the idea of hidden structures in high-dimensional data?
What's fascinating about these quarks is that they're topologically simple. You can shrink them down to a point without changing their essential properties, and yet they hold the key to the exoticness of the whole structure. It's not about the amount of topology, but about these subtle, almost invisible twists that can have really profound effects.
So it's not just about the raw data, but about how that data is connected, how it's twisted together. Maybe these quarks are like hidden relationships or dependencies within the data that are crucial for understanding the bigger picture.
That's a very insightful observation, and it really highlights one of the key challenges we face in both topology and machine learning. How do we identify and understand these subtle but crucial structures that might be hidden from our usual methods of analysis?
It sounds like we're going to need some pretty powerful tools to unravel these mysteries. What are some of the techniques mathematicians use to build and distinguish these exotic manifolds? And could those techniques inspire new approaches in AI and ML? I'm ready to go deeper down the rabbit hole.
So one way mathematicians try to get a handle on these exotic manifolds is by actually building them. It's like trying to understand a complex machine by taking it apart and putting it back together.
Okay.
They use a whole bunch of different techniques, some involving these really intricate cut and paste operations on simpler shapes. Others draw inspiration from complex and symplectic geometry.
So it's like they're constructing these exotic shapes from simpler building blocks, kind of like assembling a 4D puzzle.
That's a great way to put it. And just like with a puzzle, the real challenge comes in figuring out how all the pieces fit together and what the final picture looks like. But here's the catch. Even if you manage to construct two potentially exotic manifolds, proving they're actually different, that they have distinct smooth structures, well, that's a whole other level of difficulty.
So it's not enough to just build these shapes. You have to actually prove they're genuinely exotic. What kind of tools do mathematicians use for that?
Well, the primary tool for a long time has been gauge theory. It's this really powerful framework from theoretical physics that mathematicians have adapted to study the geometry and topology of manifolds. Essentially, it involves solving these complicated equations on these shapes and extracting certain numerical invariants that can help differentiate them.
Equations invariance. Sounds pretty heavy duty. And you said this comes from physics. I'm really starting to see how mind-bending this field can get. But how does solving equations on these shapes tell us if they're exotic or not?
Okay, think of it this way. Imagine you have two seemingly identical bells. They look the same, they're made of the same material, but when you strike them, they produce slightly different tones.
Okay, yeah.
Those tones, those are like the invariants we abstract from gauge theory. They capture these subtle differences in the geometry and topology of the shapes, even if those differences aren't visible to the naked eye. So even if two shapes look the same topologically, their gauge theoretic sound might reveal that they're actually different beasts altogether. I can see how that could be useful for distinguishing those disguised exotic manifolds we talked about earlier. But you mentioned that gauge theory has limitations.
That's right. While gauge theory has been incredibly successful in revealing these exotic structures, it's not a silver bullet. One major limitation is that calculating those invariants is often incredibly difficult. It's not a simple plug-and-chug formula. It often requires sophisticated mathematical tools and a lot of computational power.
So you might suspect that two manifolds are exotic, but actually proving it using gauge theory could be computationally intractable. That sounds like a pretty familiar problem in AI and ML. Sometimes the algorithms we need are simply too computationally expensive to be practical.
Exactly. And that's why mathematicians are always on the lookout for new, more efficient tools and techniques. And this is where things get really exciting. There are some promising new approaches on the horizon that might be particularly well suited for AI and ML contributions. Okay, I'm all ears. Tell me more about these new approaches and how AI and ML might play a role.
One particularly intriguing approach is called the slice approach. It's based on the idea that exotic manifolds can be distinguished by looking at knots embedded in their boundaries. Think of it like trying to identify different types of fruit by examining the patterns of their seeds.
So instead of analyzing the entire manifold, we focus on specific features, like knots, that might reveal something unique about its smooth structure. That sounds like a strategy we use all the time in machine learning, extracting features from data to build more efficient models. Could we use AI to automate this process of finding and analyzing these telltale knots?
That's precisely the kind of thinking that's opening up new avenues for collaboration between mathematicians and AML researchers. Imagine training an algorithm to sift through vast databases of knots, searching for those that could distinguish exotic manifolds. It's a daunting task for humans, but it's the kind of pattern recognition problem that AI excels at.
That's fascinating. So AI could be our knot detective, helping us uncover the subtle clues that reveal the exotic nature of these four-dimensional shapes. Are there any other promising techniques where AI could make a similar contribution?
Absolutely. Another exciting area is the development of new invariants that are more computationally tractable than those from traditional gauge theory. One example is the Heegard-Floer mixed invariant, which is based on a more combinatorial approach, making it potentially more amenable to algorithmic analysis.
Combinatorial, you say? Now, that's a word that resonates with us in computer science.
Yeah.
I'm starting to see a pattern here. These newer techniques in topology seem to be moving towards approaches that are more compatible with the way we think about algorithms and computation in AI and ML.
Precisely. And that convergence is creating a really fertile ground for cross-pollination between these fields. Imagine training a neural network to predict these new invariants, or to identify relationships between different invariants that might have been missed by traditional methods.
It's like we're equipping AI with a new set of mathematical senses, allowing it to perceive and analyze these exotic structures in ways that were previously impossible. It sounds like we're on the verge of a major breakthrough in our understanding of these strange hidden dimensions. But tell me, is there a way to go even further? Can we not only distinguish these exotic manifolds, but also quantify how exotic they are? Is one pair more exotic than another?
That's a great question, and it really gets to the heart of what makes this field so challenging. Mathematicians have been grappling with the notion of quantifying exoticness for years.
So it's like we're trying to develop a weirdness meter for these shapes. Is there even such a thing?
While there are some promising leads, mathematicians have proposed measures like complexity and stabilization number, which attempt to capture the degree of twistedness associated with these exotic structures.
Twistedness, that reminds you of those quarks we talked about earlier.
Yeah.
Are these measures related to how those quarks are glued in to create exotic pairs?
You're on the right track. Complexity, for example, is related to the badness of the link used to create the quark. Think of it like this. Imagine you have a tangled mess of ropes. The more intertwined those ropes are, the more complex the knot. Similarly, the more complex the link used to construct a quark, the more exotic the resulting manifold is thought to be.
So it's like we're measuring the knottiness of these exotic structures. And what about stabilization number? How does that fit into the picture?
Stabilization number is related to the number of components in the link used to construct the quark. The idea is that the more components you need to create the quark, the more stabilized and potentially less exotic the resulting manifold might be.
So a high complexity, meaning a very knotty quark, suggests a high degree of exoticness, while a high stabilization number might indicate a more tame exotic structure. It's like we're trying to understand the anatomy of these exotic shapes, dissecting them to see what makes them tick.
Exactly. And this is another area where AI and ML could potentially play a crucial role. Imagine training an algorithm to analyze the complexity and stabilization number of different quark constructions, helping us understand how these measures relate to the overall exoticness of the manifolds.
It's like we're giving AI a scalpel and a microscope, letting it explore the intricate world of these exotic shapes and uncover the hidden rules that govern their creation and classification. It's truly remarkable to think about the potential for collaboration between these seemingly disparate fields. But before we get too carried away, let's bring it back to our audience of AI and ML researchers. How could they actually apply their skills and expertise to this fascinating world of exotic, smooth structures? What are some concrete examples of problems they could tackle?
Yeah, I think it's becoming pretty clear that there are some, really deep and unexpected connections between this like seemingly abstract world of exotic smooth structures and these very real challenges that we face in AI and ML. But how can our listeners, experts in algorithms, data analysis, machine learning, how can they actually contribute to this, really exciting field? What are some concrete problems that they could tackle?
Oh, there are so many possibilities. I mean, for starters, think about the challenge of just exploring this vast space of four-dimensional manifolds. It's like trying to navigate a maze with countless twists and turns, where even the basic rules of geometry seem to break down. AI and ML could help us develop new algorithms for efficiently exploring this space, identifying promising regions where these exotic structures might be hiding.
So instead of relying on like brute force search methods, we could use AI to actually guide our exploration, like a compass pointing us towards the most interesting and potentially exotic corners of this four-dimensional world.
Exactly. And remember those quirks we talked about, those subtle twists that can create exotic pairs?
Yeah.
Yeah. Well, AI could help us develop algorithms for detecting and analyzing these quirks, understanding how they influence the overall structure of the manifold. It's like trying to decipher a secret code that's hidden within the fabric of space itself.
It sounds like we're talking about a whole new kind of topological data analysis, where AI helps us actually extract meaning from the shape and structure of data in ways that we, never thought possible. And you mentioned earlier that there are new, more computationally friendly invariants emerging in topology. Could AI actually help us like harness the power of these invariants?
Absolutely. These new invariants, like the Heegard flower mixed invariant, are often based on combinatorial structures, which are much more amenable to algorithmic analysis than the continuous differential equations of traditional gauge theory. AI could help us develop algorithms for efficiently calculating these invariants, allowing us to explore and classify these exotic manifolds with unprecedented speed and accuracy.
So AI could be our invariant calculator crunching through these like complex mathematical structures to actually reveal the hidden signatures of exoticness.
That's a great way to put it. And it's not just about calculating invariants. AI could also help us discover new relationships between these invariants, revealing, hidden connections and patterns that might have been missed by, human mathematicians. It's like having an AI assistant that can sift through mountains of mathematical data, pointing out these subtle correlations and insights that would have taken us, years to uncover on our own.
Yeah. It's truly remarkable to think about the potential for AI to not only like assist mathematicians, but also to actually accelerate the pace of discovery in this field. But it's not just a one-way street, is it?
Yeah.
The insights from topology, especially this idea of exotic smooth structures, could also inspire new approaches in AI and ML.
That's right. The existence of these exotic smooth structures really challenges our fundamental assumptions about the nature of space and shape. It suggests that there might be these hidden levels of complexity lurking beneath the surface of even seemingly simple data. This realization could lead to new approaches in areas like dimensionality reduction, feature extraction, and even the development of new types of neural networks that are actually inspired by the structure of these exotic manifolds.
So by studying these, strange four-dimensional shapes, we might gain insights that could like revolutionize the way we think about and analyze data in countless applications.
Exactly. It's a reminder that even the most abstract areas of mathematics can have, these surprising and profound connections to the real world, especially in, these rapidly evolving fields of AI and ML. By embracing these connections and fostering collaborations between mathematicians and computer scientists, we can unlock new frontiers of knowledge and push the boundaries of what's possible.
It's been a really incredible journey exploring the world of exotic smooth structures. We've seen how these strange four-dimensional shapes can challenge our intuitions about space and reveal these hidden connections to the challenges of AI and ML. I'm confident that our listeners, with their expertise in algorithms, data analysis, and machine learning, will find inspiration in new avenues for research in this really fascinating and rapidly evolving field. Who knows what groundbreaking discoveries await us at the intersection of topology and artificial intelligence. Thanks for joining us on this deep dive.